Hello, this is Byte of Code, and in this YouTube tutorial series, we're going to be making your very own emulated CPU in Python. The first thing we're going to do is to have a program file, and right now this will do nothing, but it's going to bring all the components together to run the CPU. So in the end, we're going to be importing like the memory. We're also going to be importing the CPU. And the instruction and format codes. Now, of course, these don't exist yet. So let's create that memory. What this is going to do is it's basically just going to take in a size, and then it's going to create an array of that size. So it's super simple. The reason I'm not just wrapping this in a function is because you might want to modify the array and then put it into multiple sources. So what I've done here is just make a simple for loop for and range of size, and then I'm appending the hex 0. And this is to indicate that this will actually be an array of bytes. We can't really see that in Python because this can just be a list of anything. So next we're going to be creating the CPU. And in here we're going to be making a bunch of variables. And one of those variables is the program counter. And basically what the program counter does is it tells you where you currently are in memory. This is incredibly important, so you're reading the right bytes from memory and all your programs work like you expect them to. If the program counter is at 0, it would fetch the 0th index, and then the program counter would get incremented. So then the next time we run this, it will get the 2, and then the 3, and then the 4. And the reason this is important is so we can jump around in our program. Then we're going to have a processor status, and this is just going to be a byte with all the flags. And then we're going to have all of our registers, and technically this is a register, but it's better to think of it as just the program counter. So we're going to initialize these 4 general purpose registers. If you don't know, this stands for extended, which means 32-bit. And then A, which is just a name, so it's just named A, B, C, and D. And then X means general purpose. So this is the extended A, but it's general purpose. So that's where the AX comes from. But these aren't the only 32-bit registers. We're also going to have a destination index, a source index, a stack pointer, and a base pointer. And these are going to do various things, and we'll talk about them in the next episode because we aren't actually going to use them, but I'll go briefly over what they do. The destination index and source index are for arrays. The stack pointer points to the location on the stack that we're currently on, and I'll have a full episode about the stack because it's pretty complicated, but just know that's what it's for. And then the base pointer. And this can either be the base of the stack, but we don't really care about that, so we'll just make it the address offset for subroutines. And I'll go into this in the next episode, or the one after that when we implement subroutines. Then we're going to have some 16 and 8-bit registers, all of which are going to be general purpose, so I'll just quickly get them out here. And I'm naming them like this because this is A, general purpose, and I'm labeling them the same even though they aren't correlated in any way. And then I have this, but instead of just being normal or extended, it's going to stand for byte. So this is going to be B, which is byte, so it's going to be 8-bit, and then A, and then X, which is general purpose. And then this is just a general purpose, so it's going to imply that it's 16 bits. But this is not the only things we need to get this CPU working. We're also going to need an internal copy of the memory, and technically you don't need this, but I'm going to do it because it's going to make it a lot easier, so we can just do self.memory instead of having to pass it into every single function that we call. The con is that we can't manipulate the memory while the CPU is running because it's taking its own copy. But that shouldn't be a problem for a while, and once we get that far in, we can easily change it. And you notice that I'm just extracting this, so I'm basically treating this as a function that will just return this array, because we're creating a new instance every time anyway, so it really serves no purpose to make our lives harder by having to reference self.memory.data every single time. Then we're going to have a buffer, which is going to use for error detection. Basically, it's just going to detect if the program counter is about to exceed the max memory. So then instead of getting a index out of range memory in Python, we can throw a custom CPU error, which will be like invalid, or basically just same index out of range, but we'll probably call it like out of memory or segment fault or something. Then we'll have a debug mode, which we will use in this episode, but it's going to default to off. Then we're going to have cycles, and this is basically going to limit the CPU. It really means clock cycles, and what that means is everything's going to consume a cycle whenever you read or write memory or registers. Now, this is because on the hardware level, you want to keep everything on a clock basis so that things don't go faster than you expect, and then the other things are far behind because of a race condition. We'll also have an interrupt, and this is going to be false. And we don't use this until next episode, so I'll go more in depth in how this will be used. But it basically means if we've detected an external interrupt and we're currently inside of it. Now the last thing we're going to need to do is create a flags class for this processor status. And what we're going to do is create a flags class right above here. We'll just put it in the same file because it's going to be really small. And it's going to initialize 8 bits. So the 0 flag, the carry flag, the overflow, the sign, busy, trap, interrupt, disable, and interrupt. So we have all of them here. So this basically be ALU turns 0 result. So the ALU gets pointed to whenever you want to do addition or subtraction or any math. It stands for arithmetic and logic unit. So it gives, but it's also logic. So if you do like an AND instruction or a bit shift, it will also count for that. And it will be on when the result is 0 and off when it isn't 0. This is basically going to be an overflow, but it can also be used for joining together adders to make them bigger. So combining two 32-bit to be 64, and the carry will just basically go down the line and connect into each other. It's also the borrow and subtraction. The overflow, on the other hand, is similar, but it only gets triggered if the carry in and carry out are opposite. Now the sign is basically negative flag, so it's on if the result is negative, with the ALU, of course. And then none of the rest actually deal with the ALU, so I'll separate them like this. We have busy, which is basically if you're chaining together cores or CPU instances, and one of them is handling with a register, so the rest of them need to wait, so then they get the updated register value, it will call busy, and then the other ones will be like, oh, okay, we'll wait. This is basically the trap. I didn't name this, it's a convention, but it's basically just single step. It's like a debugger built into the chip, and that's really cool because it helps you debug programs by going one address at a time. Then we have interrupt disable, and this is not an interrupt, it's basically if you want to disable an interrupt. And this is like if you're in the middle of doing something with CPU and you don't want key presses to do anything, you can be, oh, I'll trigger the interrupt disable. All of those external shenanigans will not affect what I'm doing at all. Then we're going to have a detected interrupt. And this isn't an interrupt because it's basically just you will turn this on externally if you're going to fire an interrupt. So it's basically going to be there is an interrupt. And it's going to be on. And then this will turn on when we've actually acknowledged the interrupt. So we could turn this on and interrupt disable, and this would never get turned off essentially because it's never being handled. Now we're going to make one more function, and this is going to be full. This is basically going to just combine them all into a single byte. We aren't going to use this until we start unit testing, which will be in the next couple episodes. But it's very important if you want to compare the entire byte instead of having to be like, I'll compare the Z flag and then the C flag and then the O. It makes it a lot faster. So we'll just return all of them strung together. This will be the most significant byte, and this will be the littlest byte. So this will be the 128, then 64, and then 32. And the way I'm doing that is I'm going to shift them each over n amount of bytes and then OR them all together. And now that I've done this, you can see exactly how I did that. And we're just using the OR, and we're ORing together this, and then the shifted 1 over, and then the shifted 2 over, and etc. And we'll just return that. And I guess you could just do this if you wanted, but I'm going to store it in a variable to label that it is a processor status to just make it a little more clear what it's doing. So we'll just create an instance right here. And that's done with the initializer stuff. Now if we wanted, we could come over and make an instance, and that's actually what I'm going to do, but it can't do anything right now. So first we'll be able to load memory, and that's going to be the first function. It's going to be a really simple one too. It's going to return nothing, but it's going to take in a memory. And we can actually just copy and paste this code because it's doing the exact same thing, but instead of creating a new instance, we'll just take the one that was given to us. And that's the entire function. It just resets the buffer and then resets the memory. And the reason we want to do this is so we can externally edit the memory and then load the memory in the CPU after we've already edited it. And the reason we could do this is so we can put it into multiple places. And we can actually have like a copy of the CPU, and then we can load it into both. And then we don't need to change it at all because we're loading in just an instance. And then we can print the memory. And it should have taken full effect because we're actually loading it at this point. But of course we get an error because we actually haven't defined inst codes. So let's just do that right here. Now just to get this working, we'll just define a couple variables. And these are going to be our instructions. And we're going to be using NOP in this example. And we'll do move. Now if you're wondering why I'm giving these hex values, it's because I predefined a bunch of values I want to give to these instructions. In a separate sheet, I came up with about 100 for our CPU. So I'm just going to reference them here. And these happen to be 0, 1, 2, 3. In this episode, we'll implement these two. And then in the next episode, we'll implement these two instructions. Now that is working, we should be able to get 2 2s. And that's exactly what we want. Now in the CPU, it's not actually doing anything. It's just loading the memory. So these no operations are doing nothing. And we can take out this copy for now. And we really don't need to print this because now we know it's working. So in the CPU, let's actually do something. I'm first going to make a fetch byte instruction because we're going to use this shortly. And this is just going to return the next value in memory. And this is going to take advantage of the program counter. So it's going to index the program counter from their memory. Then it's going to increment the program counter. So then the next time we call the same function, it will get the next one, program counter plus 1. Then we're going to decrement the cycles because like I mentioned, you consume a cycle whenever you read or write memory. And we just read from memory. And then of course we'll return the value. Now let's use that. We'll pass in some cycles, and I talked about this already. And this is so we can limit the CPU and basically want to give an initializer for the cycles like this. And then we're returning any. And the reason I'm doing this is because I'm actually importing from the typing module. So I'm importing from this typing module, and what I'm basically going to do is I'm going to show you this command line argument you can pass into Python to install this for yourself if you don't already have it installed. And I already have it installed, so it's not going to do anything, but it will install for you if you don't have it already. And this just gives you a nice, clean any type. So now that we have that all settled out, we can actually make a return value. And we're just going to return none. But not always. If we're debugging, we don't want to return none. So if debug mode is enabled, we're going to return basically something for unit test, basically how many cycles were consumed. So ret will equal cycles minus self.cycles. So if it succeeds, and the right amount of cycles were consumed, so this would decrement all the way to 0, it would just return what you passed in. Now I can make the loop, and this is basically going to stop once the cycles are gone. It's going to take advantage of this fetch byte I just made, and it's basically going to just let you get the next byte from memory. So why don't I just print the hex of this instruction, and then we'll do nothing else with this. And immediately we can start seeing some results. If you just call the execute with 1 cycle, we should just get a 2 in the terminal, and we do, so that's working. But this isn't very exciting. We actually want to do something with this value. So we'll make a big switch statement, or just an FLF statement in Python. And it's going to be NOP. And of course this doesn't actually exist, so let's import that. And for NOP we're going to do nothing, because it's no operation. We'll also do halt, because it's super easy. It's just going to return. And boom, we already have 2 instructions done just like that. Given they are the simplest instructions, but we still have them done. So now when we do this, it will do nothing. But if we have multiple instructions, like if we have a NOP here and here, well, if we put nothing here, or just gibberish, it will just do nothing right now. So it's going through the NOPs, and then it's doing this, but that's not really what we want. We want some basic error detection. So we'll just print a nice formatted message. And we'll just pass in the hex of the instruction, and the hex of the program counter decremented. And this is because we're incrementing it and then using it. The address that we're getting here is actually 1 greater than where the instruction was at. So if we did it like this, and then we get an error, it won't be exactly what we want. And this is not working because we didn't give enough cycles. But it's saying 0x3 at address 0x3, but it's actually at 0x2. So we do need to decrement this. And now this should be working exactly as we wanted. We get an error, and we can test our halt instruction, and this should just make it return, so we don't get an error. So that's exactly what we want. So that's all for this episode. In the next episode, we're going to be implementing the interrupt instruction and the move instruction. And after that, we should be able to get hello world printing in the terminal, which is really cool. Thanks for watching.